Now let's understand how does the color magnitude diagram evolve along the life of a group of stars. So let's assume that all the stars in a cluster were born exactly more or less the same at the same time. Well, all the stars align along the main sequence. So from top blue, big, bright to uh, bottom right, which is red and small. As time goes on, there are more and more stars aligning, but the very bright stars on the top left reach the end of their life. We have seen previously that the blue stars are big and bright and they emit much more energy than the red stars, but this has a consequence on their lifetime, which is much shorter. So as they reach the end of their life, they start to migrate over the color magnitude diagram, moving from left to right. And as time goes on, as you can see here, more and more stars leave the main sequence. So this depends just on the time. So after 12 million years, probably the situation is this one. After 30 million years, the situation is this one. Time goes on, and the critical point here moves due right, meaning that more and more stars are removed from the main sequence and go to the red giant branch. As you can see, more and more stars migrate. And after 2 billion years, some of the stars go into the white dwarf branch here on the bottom left. Time goes on, and this bending here of the main sequence, which is now completely disrupted, this point here, which is called the turn-off point, moves to the right as time goes on. And when the cluster of stars is very old, then we are in this condition here. So actually, it's just needed to measure the point at which the color magnitude diagram bends, so namely this point here. This point tells you what is the age of the star which is the next to disappear from the main sequence. In other words, once you know the lifetime of a star here, you know the age of the whole cluster of stars. As time goes on, this point here moves to the right in the B minus V diagram. I remind you that the B minus V diagram is just a way to convert the color into numbers. In other words, B means the measurement in the blue light, V means the measurement in the visible light. So we make this subtraction and we get a number here, telling us that the color can be converted into a number. So this is an easy way to obtain the age of a cluster of stars, and very useful if we want to date the objects we see around us. So the star life can be resumed as a series of events. We have a birth. In this case, we see the Orion Nebula. In the Orion Nebula, we have a region on the top left, which is exactly what we can interpret as a bubble expanding. And so this bubble means that there is a young star there which is emitting a lot of ultraviolet radiation. This ultraviolet radiation clears up the space around it. Then we can say that there are places in the universe that we can call nurseries because they are just giant molecular cloud with dust, and they can host a lot of material, and this material is what is needed to create the stars, to produce the stars. What is interesting is that despite they are very cold, so 10 kelvins, and very dark, they are much denser than the rest of the interstellar gas, but much less dense than the atmosphere we have on this planet. So this means that actually we call it a cloud, but it's not even uh, as clear as would be the normal atmosphere for us. So it's dense in terms of universe, but it's not dense compared to what we are used with. What this hydrogen gas surrounding the clouds can glow and can be visible, and we can see it in H2 region, which is the ionized hydrogen region we can see in the sky. Well, after that, there is a period when the stars are young. We can see here two pictures of the same region in the Orion Nebula again, which is our nursery, as we have stated before. And on the left, we see the visible, and on the right, we can see the infrared. So there is something behind the cloud, meaning that the stars are evolving. Um, another very famous example is this one, the pillars of creation. These are also called the fingers of God. And if you click here, you can see how is this picture developed. As you can see, this is a picture, the final picture of the fingers of God, the pillars of creation. And what we can see here are actually star-forming regions. So there's the nursery we have mentioned before. Well, at the beginning, this picture was made with 3 different pictures. And so let's have a look on how this picture was developed. So this fraction of the picture, which is the top right here, is actually this picture we see here. And all the dots we see, the white dots we see, are the noise. So the photons hitting the plate, because we need a long exposure to take these pictures. And if you want to eliminate this noise, you have to take 2 pictures and then make the difference between one and the other. So for example, you see that from one picture to the other, some of the white dots disappear. So for example, have a look at this part here. We take another picture and there is nothing. So this means that we can easily eliminate part of the noise. Once you have eliminated the noise, this is the picture we get, which is far from being colored. Well, after that, we apply various filters in order to obtain some color. How do we do that? Just by comparing the light we obtain with the usual emission we would have from some particular element. And so this is the original picture for the plate number 2, for plate number 3, for plate number 4. You see they are black and white. And even if you look at the sky with a telescope, you would only see white things, except for some particularly bright and close object. Otherwise, you won't see any color. So this is the real picture with a little bit of correction. And then we add the color, and the color is added by looking at different filters, which can be in the visible, in the infrared. And so we apply these different filters and we get different shades. And finally, these filters are colored, and once we color them, we get the final picture by adding particular uh, amounts of colors for each filter. When the stars reach their uh, adolescence, in some sense, they become uh, angry as all the adolescents, and what happens is that they emit strong winds from the north and the south pole. These jets are clearly visible within those pictures. So from this picture to that picture, we are zooming in the jets. You can be really, really extended, as you can see in the first picture. And when you get closer to the stars, you see where they are emitted from the core of the cloud we see here, which is just the emission of a single star in this case. So these are called the T-Tauri winds. So just to resume, in the main sequence we have only stars in between 0.08 solar masses and 100 solar masses. And 90% of stars' life is in the main sequence. The main sequence then is not evolutionary, so from top left to bottom right, the stars do not move until they die. Once they are produced, the stars do not stay there. They can interact with other stars, and so somehow they move apart and they may form multiple systems or binary stars, as we have seen before. 2/3 of the stars have one or two companions, so this means that most of the stars live together in some sense. And at a given moment, they can interact with each other in a way that one of them will eat the other one. And we'll see that in a later class. What happens when we extend a little bit the mass limits of stars? So we can have brown dwarfs when the stars are really small. In this case, we see the star Gliese 229b, which is actually a giant gaseous object which emits light. It's very similar to our Jupiter. Jupiter emits light because it is very massive and it has an intrinsic energy inside. So these are stars, these are in some sense planets, very big, and they can emit light. So they are in between the concept of star and the concept of planet. On the other hand, if you have a too big star like Eta Carina here, then it emits the excess of mass, which giant puffs. It blows out part of the mass to reduce its mass to a sustainable amount of matter. Once the star reaches its final age, the hydrogen was all converted into helium. At a given moment, the nuclear reactions stop. When a nuclear reaction stops, there is a sudden collapse. This core collapse and the other layers bounce back because of a new pressure. How does happen? It does happen because you have a strong pressure, increasing pressure, and this increasing pressure triggers a new nuclear reaction, which involves now the helium you have in the core. And so at this point, strong winds blow out part of the matter. So this makes that right before dying, the stars make somehow a breath, and so it makes something like that, which makes it a variable star. And so what